Assalamu alaikum, صبايا وشباب. Uh, again, before I will start fully with the banked curve, I like to visit one last problem, and it's a problem, this problem 8. Just for you to know that even if the problem doesn't ask about straightforward velocity or acceleration or force, it could be asking about something like a static friction, and it should be all right. So again, I'm just reminding you, we are talking about a horizontal circle or a horizontal turn. So here it says how large must the coefficient of static friction be between the tires and the road if the car is to round a level curve of radius. So we are on a normal flat curve of radius, just a second, okay, of radius is equal 125 meter and a speed of 95 kilometer per hour. Here, of course, pay attention to this, please. It is not in SI units. This is kilometer per hour. We have to convert it into meter per second. This is one thing you have to pay attention to. But first, let's figure out what we are trying to find. The problem is asking for µs. Okay, you have no formula that you memorize to find µs. And this is what I'm saying. Don't even memorize the formulas for V or anything of that matter. What we have here is a car, and this car is negotiating a curve, okay? It's negotiating a curve, and it's a flat curve. So what we have, if you recall, that we have this Fs, which is exactly also the centripetal force. So in the horizontal curve, flat curve, the rule that we should follow, that we have the same force, which is the static friction, and I should write it even like that, right? Because it's static friction, is equal to the centripetal force. The centripetal force is ma radial or centripetal, which is mv square over r, okay? And this is mu s, you see, mu s come. So we don't really need to be tense or confused when we say, oh, the question is asking about static friction. We have no idea. We have no formula. No, this is our main formula. It is the static friction is equal to the centripetal force. So it's times Fn. And we know from the free body diagram of the car on the curve that this is Fn and this is mg or fg, and the car is going on the road, okay? And there is no movement along the y direction, so Fn is equal to mg. So it's mu s times mg. Great. So m will cancel out with m, and what is mu s? It's equal to simply v square over r times g. This is not a formula to memorize. I wouldn't. I will just say this. Maybe you can jump from here to there. That's fine. And then you calculate it. Okay. And now, once we reach here, we have to convert the 95 kilometer per hour into meter per second. Do you remember? Let me do this. And let me convert 95 kilometer per hour. If you recall how I used to convert, we say 1 hour has 60 times 60 seconds, right? And times here, okay, another factor for the kilometer. 1 kilometer is equal to 1,000 meter. So of course kilometer will go with kilometer, an hour will go with an hour. So it is 95 times 1,000 divided by 3,600, and the value 26.4 meter per second. You plug this velocity here, and the value of mu s will be 0.56. This always will be less than 1. So it's a coefficient which is less than 1. So if it's more than 1, you have to review your calculations. So this is a nice problem to show you that this is our basic equation that we are dealing with. Okay? Now enough with these problems, and now come back to the banked curve. Again, as I mentioned at the end of last clip, that the banked is basically, earlier we used to talk about a car which is negotiating a simple flat curve. In this situation, the curve, if you see that there is elevation, you see there is elevation with an angle from the horizontal of theta. This is called the banking angle. So now we are really concerned to calculate or to find that kind of angle. All right. It is very important for the engineers to be able to do these kind of calculations. Now, if you recall, guys, it looks something like an inclined plane, right? But again, the movement is not up or down. So it's not exactly our usual inclined plane problem. If you recall, from the beginning of the chapter, I mentioned something that it is kind of inclined plane because we have an angle, okay? But we are, if you take a cross section of the curved road or the banked curve, this is basically the car moving towards you or away from you. In this situation, guys, in this situation, the vertical will stay the vertical. So this is our y-axis, and this is our normal horizontal x-axis. Okay, this is the major difference between the inclined plane. Let me just erase this one for now. Here, okay, between the inclined plane and the banked curve. If you remember, in the inclined plane problem where the movement is either up or down, this was our x-axis and this was our y-axis, if you recall. All right, this is the inclined plane problems of chapter 4. Okay, so this was the y, this was the x, because we moved our axis with the angle of the inclined plane. This is because of the movement. Our movement is on the x-axis. But here, our movement is not simply, like the car is not really moving on any of these axes. It's not going up or down or even up or down. It's literally moving into a horizontal, in a circular motion. So here we change the axis because the car is moving on this axis. Here the car is moving into a circular motion. So I really don't care. I don't want to change the axis. This is the vertical to the ground, which is the normal vertical, and this is the horizontal, which is the ground without the angle. This is the flat. So in this situation, we have our original x, of course, you know, x in both direction, and y, of course, in both direction. Okay. So this is the major difference between inclined plane problems and a banked curve. In the banked curve, y is y, x is x, nothing is rotating. All right. Now, what is rotating? It's the road itself, from the horizontal to an angle. Now, if you see the angle that the road is moving here is the same as this angle, where basically the vertical is becoming in this angle. Let me make it more clear to you. Remember one thing. What is the definition of the normal force? Wherever the surface, the normal force is perpendicular to that surface. If the surface is like that, it's perpendicular to that surface. Oh, the surface is like that. It's inclined. So where is the perpendicular? Where is the Fn? Is it on the y-axis? No, this is the normal. Wow. Okay. So this is our surface, and this is perpendicular to the surface. Where is Fg? It is downward, as usual. Okay. So the first thing you can see that now Fn is the force with an angle with respect to the vertical, while Fg is simply along the negative y direction. All right, you see here the Fn was with the y-axis, so it has no components, and mg has an angle with respect to the y, so it has components. Here Fn is with an angle with respect to the y, and mg is exactly downward. So we will decompose the Fn this time, not the Fg. You got the idea, guys? This is a very important slide because it shows you that the vertical is the original vertical because of the car movement. It's not the car movement which starts going into a different axis. It is the ground itself. It's the ground which becomes from horizontal into a banked angle or a banked curve. So this all horizontal moved with an angle of theta, okay? And if you imagine this curve or this road, the perpendicular to the road is this one, which is also with the same banked angle with the vertical. But Fg is downward, which is with the y-axis, so we don't have to compose it. And basically, this is what I am explaining, that this is the Fn, and now it has two components, as we know, because it has a theta. So this is the adjacent, which is Fn cosine theta, and this is the opposite, which is here. So it's Fn sine theta, and mg has no components because it's literally on the y-axis. Guys, we should remember, where is the acceleration which keep the car moving along this circular path? It is the acceleration towards the center, the centripetal force. So, in case, if I just want to explain Newton's second law, F is equal ma. And we always say that F is F sub x and F sub y, where we don't have F sub x here. We don't. The summation, we have forces along the y-axis, and we know that there is no acceleration along the y-axis, so this all equal to 0. What are the forces along the y-axis? Up minus down, Fn cosine theta minus mg is equal to 0. Good. So this is one equation. Now, is the car moving along the x-axis? No. There is something called, basically, whatever that movement along the x-axis is that which keeps the car moving in the circular motion. So it's ma. This is the difference here. Okay? It's not anymore ma sub x. It's the centripetal force. So back to this equation, which is written already. What are the forces along the x-axis? It's only Fn sine theta. So if you see, what is the force which is keeping the car moving into a circular path on a banked curve? It is the x component of the normal force. It's the x component of the normal force. So this is the cause of the motion. This is the cause